Well, congratulations folks, you made it this far, and the final lesson in maths methods for 2021 is on the confidence intervals for the population proportion, and it's a doozy. Alright, so let's go through the general idea before we get into some examples. So different samples can have different values for p hat, the sample proportion. So we know that if we're looking at, say, number of students with brown eyes and we take a sample of 10, we might get 5 with brown eyes in the sample, 6 with brown eyes in the sample of 10, 7, etc., etc. So if we know what p hat is, that is, if we know the sample proportion, what can one sample tell us about p, the population proportion? So say if we knew from a class sample that 25% of the class buy their lunch, what does that say about the proportion of the whole school that will buy their lunch today? So that would be interesting. That would be fine. Then we could sort of use the sample to actually make observations or kind of get an idea of the whole population. So using confidence intervals, we can state how confident we are that a population parameter p will lie in a particular interval, so between what values. So it's important to remember distributions of the sample proportion are normally distributed, with the expected value of the sample proportion being the population proportion and the standard deviation of the sample proportion being this formula here. And again, both of those, that and that, are on the formula sheet. So in a sample of 30 students at SAC, 5 wear glasses. What's p hat? Well, p hat is the 5 students wearing glasses out of a total of 30 students, 1 in 6. Now, we don't know what p, the population proportion, is, but we do know that p hat, the sample proportion, is approximately normally distributed, so the distribution will look like that. So let's take a punt, i.e. what we're going to do is, based on knowing that p hat will be approximately normally distributed, we're going to use this idea to try and get an estimate of the population proportion. Okay, to do this, we need to again recall that the best estimate of the standard deviation of the sample proportion is this, and then go back to normal distributions and remember about z-scores. Right, so remember, to calculate a z-score, what we do is we look at our value. Just say on a test you got 40, and you knew that the mean on the test was 35, and the standard deviation was, say, 5. That would be 5 over 5, which is 1. That means you're 1 standard deviation above the mean. Okay, so that's how we use this formula here. So linking in with this topic, the z-score can be found by subtracting the population proportion from the sample proportion and dividing by the standard deviation of the sample proportion. So that's what this is doing here. This is the sample proportion. Now, the expected value of the sample proportion is the population proportion. What we're doing is we're removing that from the sample proportion, dividing that by the standard deviation of the sample proportion. So the next step in the formula, and what we're doing is we're basically deriving a formula that is on your formula sheet, so I'm explaining to you how it's derived. So we simply replace the expected value of the sample proportion with the population proportion and the standard deviation of the sample proportion with its formula. Now, why are we doing all of this? Remember that we're trying to find out about p, the population proportion. So what we would be doing here is solving the above this value for p. Now, here's where it gets interesting. So we know that for a z distribution, between these two values will be a probability of 95%. So 95% will be between these two values. And I'm just going to prove it to you by quickly running it through. So I'm just going to do continuous norm CDF, where my lower is negative 1.96 and my upper is 1.96 for the z distribution. And we get 0.95. Alright, and what we just did earlier is we said that z is this thing here. So all I'm going to do is replace this z with this. Okay, now what we'll do is multiply both sides by this thing here. So 1.96 gets multiplied and negative 1.6 gets multiplied. So that gives us this line here. Now, what we're going to do is get P in the middle. So we're going to subtract P hat and subtract P hat from here, and then divide by a negative, divide by a negative. Ultimately, it leads us to this line here, okay, that the population proportion will be between this value here and this value here, and we are 95% certain that we would have captured it. All right, so conclusion, we can be 95% confident that P falls between this lower value here in the interval and this upper value here in the interval. And more formally, this is what it looks like on your formula sheet. Saved, so the final item on the formula sheet saved for the very last lesson. So back to the original question, in a sample of 30 students at Sacré-Cœur, 5 wear glasses. We don't know what P is, but we can use these formulas here to get an idea of, or state how confident we are that P falls within a particular interval. Now, just one big disclaimer here. In order to use the rule to calculate the confidence interval, NP and N multiplied by 1 take P must be greater than 5, i.e. it assumes then that if it's above 5 and at least 10 is ideal, then what we're actually working on is something approximately normal. Okay, so here is our first example. Find an approximate 95% confidence interval for the proportion P of Catholic secondary school girls who wear a ribbon. If we select a random sample of 20 girls, find the value of P hat to be that. Right, so I'm just going to go straight to the formula. P hat, take away. Now, 95% confidence is, as the example suggested, up here, 1.96 gives us 95% confidence, times P hat times 1 take P hat all over N, and then the upper one is plus. Right, so all we would do then is just fill in the values. So 0.7 is P hat from here, the sample proportion. N is the sample size, 20 plus. Okay, so now what we would do is bang them into the calculator. So it's 0.7 take away 1.96 times shift root, shift divide, 0.7 times 0.3 all over 20. Alright, so the lower is 0.49 ... upper, pretty simple, you don't need to type all that in again, you just change that to a plus. That's 90.00 ... Okay, what does that suggest? Okay, we are 95% certain that the value of P is between 49% and 90%, roughly. Okay, so again, another disclaimer on how to interpret that interval. What we know is that the probability between 0.499, that first value we found in the interval, and the upper value in the interval, if we look at the probability that P is between these two equals 95, that's not the case. Okay, so since this confidence interval is based on one particular sample, okay, so the sample in our case was, it just so happened that 0.7 of 20, so that's 14 out of 20 girls were wearing a ribbon in that particular sample. Important to note that the value of P may not lie in the stated interval. We might have got just a bizarre bizarre sample, and so when we did our operations on it, it just didn't work because of the weird sample. So the correct interpretation of the confidence interval is that we expect approximately 95% of such intervals to contain the population proportion P. Okay, so if in this case here we are 95% certain that the value of p is between these two values, another way of looking at it is if we generated a number of, or 100 intervals, 95 of them would contain the population proportion. Now that's hard to get your scon around, so this diagram actually is the thing that explains it best to me. So whether or not the particular confidence interval obtained contains the population proportion, we generally don't know, because we don't know what the population proportion is, nor will we ever really know. All we can be confident in, or with 95% confidence, that we have captured it. So the diagram right shows 20 different samples, and P, the population proportion, is constant. It is constant, it's always constant. So we can see here that P is here for all of the samples. The red dot shows P hat, so this is P hat here. And we can see that the confidence interval here actually captures the value of the population proportion. So this is P hat. We say that we are 95% confident that it's between these values here, and it was. Here's P hat, 95% confident that it's between these values, and it was. So tick, tick. P hat, 95% confidence within, and it is. Now this one's an interesting one. Okay, we got a value of P hat here, and we said that we were 95% confident that it fell within this, and it's not true. Okay, so we were 95% confident that we got it. In this case here, all the intervals except one, 19 out of 20, or 95%, have captured the value of P. And we expect this. We know this will happen with a 95% confidence interval. We may not get it. We're 95% confident that we're going to get it. All right, another example. A survey found that 237 out of 500 UGrad uni students questioned intended to take a postgrad course in the future. We want 95% confidence interval for the proportion of undergraduates intending to take a postgrad course. So P hat in this case is the 237 out of 500. Okay, and again, to get the 95% confidence interval, we'll go straight to the formula. Takeaway rather, 1.96 times P hat times 1 take P hat over n, then P hat plus 1.96 times right, so again it's going to be a case of slamming this in. So 237 over 500 is P hat. N was the sample size, which was 500. And then we just write the same thing. It's a little tedious, actually. There is a quicker way, I'll show you in a sec. Okay, so I could type all of this into the calculator, okay, or I could use this, and this is a really quick way of doing it. For a 1 mark question, I would absolutely be doing that. So that little graphic down the bottom suggests we go to Menu and Statistics. We hit a part of the calc called Interval. We go to 1 prop Z. All right, now 1 prop Z says, give us a confidence level, please. Well, we want 95% confidence. It says, hey, what's the sample size? And what is observed in your particular sample? So we observed 237 in a sample of 500. And here's our confidence level, or interval rather, 0.43 ... up to 0.51 ... Now notice that the interval itself is between 43 and 51. You might notice or compare that to the interval we got here, which was massive. And what happens is we get more and more we get a smaller interval when we sample more people. So notice that this one here has a sampling 500, the other one had a sampling 20. Now the more people we sample, the better p hat approaches p. That is, the sample proportion will get closer and closer to the population proportion the more people we sample. That should make sense. Okay, if we only sample a few people, just say that there's 1 million people in a country and I sample 10 to get their ideas, I'm not going to be very confident in my results from a sample of 10 to kind of talk about the entire population. Alrighty. And again, let's just interpret this. We can say something like we can be 95% confident that P is between, so the population is between roughly 43% and 51%. You can use the decimal, you use a fraction if you really want, if it approximates to a fraction or goes to a fraction. All right, now we've been using 1.96 as this value here in our formula. Now on the formula sheet, let's go back to that, it's listed as Z. All right, well, what if we want a different level of confidence? What if we wanted 68% confidence? It's fairly easy to change this value of K to the appropriate confidence level by thinking about the normal distribution curve. So if we want 68% confidence, what we do is we go, all right, so that's 68 there. Either side here is going to be 16 and 16, which adds to 32. Then all I'll do is use my calculator and inverse normal CDF. I'm going to get a right tail probability of 16%, or 16 out of 100, for the Z distribution. And that gives us K value of 0.994457 ... Okay, that means that this value here, roughly 1, okay, what we're going to get is between 1 and -1, a confidence level of 68%. That should make sense because 68%, either side of the mean, is 1 standard deviation. Right, well, what about 90? Okay, if we got 90, that side is 5 and that side is 5. So all I do is I just change this value here to 5, and I've got my K is 1.64485 ... 95, we know that that's 1.96, but how did 1.96 arrive? This is 2.5 and this is 2.5, so we're going to change that to 2.5. Oopsie. Take 2, K equals 1.95996 ... roughly 1.96. What about a 99? That's 1 on either side. No, it's half on either side. So K equals 2.5758 ... Now note your textbook gives you those, but you don't get those in the exams. So you're going to have to know how those values are obtained. All right, so find an approximate 90 and 99% confidence interval to 4 decimal places for the proportion P of school children in Australia who are left-handed if we select a random sample of 30 children and find P hat to be this. So by formula for 90%. Okay, so to get it, what we'll do is use the formula. Okay, I just went and copied that formula, so should be able to paste it. Right, there it is there. All right, so I'm not going to rewrite the formula this time. I'm going to try and punch this out a little bit faster. So it's going to be P hat 0.4, take away, now Z for 90 is going to be 1.64. I can't really read my own writing. 1.64. dot 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 times 0.4, 0.6 all over n, which is 30, comma 0.4 plus 1.64 dot 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 times we know what n is, come on, 30. Okay, so here, if we type this in, 0.4 take away so I'm sort of being a bit loose with my approximations here. Right, so there it is by formula. By CAS will involve us using one prop Z, so let's just go for it. Stats calc interval, what is it, 90. So we need the sample, or the number in the sample, which is 0.4 of the 30, and the sample size is 30. And of course, so one prop Z int is the program, right? And basically we just got those. All right, now let's do it for 99. Okay, so by formula for 99, I'm not going to do it by formula. Let's just do it by CAS. What will be interesting, let's just have a think about, okay, so if I want with 99% confidence, what the formula will do, what this thing will do is actually stretch this interval out a bit more. Because if you want to increase the confidence, that is, if you want to get a better approximation of P, then you've got to increase the sample size, or if you want to get this higher, like a 99% confidence, what it will do is it will respond by actually giving you a larger interval to be sure that you're going to capture it in 99%. So let's just see what happens. So it is 0.169 dot dot to 0.630 dot dot dot. Right, so between 17 and 63% versus 25 and 54%. So to get the 99% confidence interval, it's just stretched it out a little bit further. How much further? That much further. Right, determine the 85% confidence intervals, if that is that by CAS or by formula. Right, so while we're in one prop Z, let's do it by CAS. Um, 0.7 of 200. There it's 200. Okay, so it's 0.653, 0.746 via one prop Z, and the formula, alright, well we'll do it I suppose. Alright, what's 85? Oops. So 85, so we're going to go right tail. 85 means 15 left over. Half of 15 is 7.5. Okay, so this value here, the K or the Z, is going to be 1.43 dot 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 times 0.7 times 0.3 all over 200. 0.7 plus 1.43 dot 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 times and just for effect I'm going to do this, okay, but I know it's going to work out in terms of what's on the right there. So 0.7 take away this value times shift divide, shift root, then shift divide, 0.7, 0.3, 200. All right, so there's our lower confirmed, and our upper will be plus that, 0.74 confirmed. Okay, so that will just go there. Okay, but again, notice how I got the 85% by showing a calculator move on that. Okay, so precision and margin of error. So if we wish to narrow the range of confidence of the confidence interval, then we need to increase the sample size. Okay, again, if the sample's massive, then we can have, or the confidence interval will be smaller, because we know that, again, as the sample size increases, then it'll approach P. As this gets bigger and bigger and bigger, it just becomes P. And that means that, you know, our 95% confidence interval will be like really small, because we know that we just sampled a huge amount of people. So we can assume that P is within there, and we get this smaller margin of error. So you may have heard in the media during election time, we predict the proportion of people who to vote for the Greens to be 72% plus or minus 2%. So it's called the margin of error. The smaller the margin of error, the narrower the range of the confidence interval. And to reduce the margin of error, or to get a smaller margin of error, we need to increase the sample size. So the distance between the sample estimate and the endpoints of the confidence interval is called the margin of error. Right, so basically what happens is we get a sample proportion p hat. Either side of that, we're going to get an interval, which then gives us an idea about p, all right? And the distance from there to there will be the margin of error, okay? And that's why that should look relatively familiar. That, again, is just part of this formula here. It's this little bit of it here. This bit is that, okay? So we take that out, or we just use the right side. It doesn't really matter which side you use. All right, so let's put that into play. You don't get the margin of error formula, but you don't need it. It's part of the confidence interval formula, which you do get. So determine the sample size required to achieve a margin of error. So M is equal to 0.3 in an approximate 95. So 95 was 1.96 above. Times p hat is 0.65, where n is the thing that we don't know. So what I would do is just chuck this into the calculator and solve for n. $971. .071. Therefore, 971 people. So if the survey has 971 people in it, we're going to get a margin error of 3% with the 95% confidence interval. What's that doing there? All right, so calculate the 90 and 99% confidence interval and the corresponding margin of error for the proportion of secondary school girls who wear a ribbon to school if we select okay, first cut point is here. For this example, we are going to calculate a 90% and 99% confidence interval and the corresponding margin of error for the proportion of secondary schoolgirls who wear a ribbon to school if we select a random sample of 200 and have a p hat of that. Right, so let's get the 90% and 99% here. Then we'll get the margin for the 90 and the margin for the 99. Then we'll answer the next question. Okay, so to speed up the process, I'm absolutely going to use stats to get the 90 and 99 margins. So menu, stats, calc, interval, 1prop_z. So we want a 90% confidence interval. Sample, or the number in the sample is 63% of 200. And in the sample is 200. Okay, so that's going to be All right, now to calculate the margin of error, all we're going to do is from the upper, we're going to remove p hat, or from the lower, add p hat. Either way, it'll be exactly the same thing. So I'll copy that, go into the main and go that, take away this sample proportion. So the margin of error is going to be 0.056 ... Right, you could easily do that with the margin of error calculator as well, or the formula, but if you understand p hat sits in the middle of these two values here, so all you need to do is either add p hat to this one or subtract p hat from this, and you got it. Right, we'll do the same thing for the next example. So stats, calc, interval, 1prop_z. Now this time we want a 99, 200 in the sample. So as you would expect, the interval is larger for a higher confidence level. And the margin of error, let's just do it a little differently this time. We'll take that lower value, copy it, and add the value of p hat to it. That's not right. What we'll do is we remove that from p hat. And there's our margin of error. All right, what would the sample size need to be so that a 99% confidence interval had the same margin of error for a 90% confidence interval with the same value for p hat? Okay, so the margin of error is here. We want the margin of error to be this. So that needs to be a margin of error. Now, what we're going to do is we need a 99% confidence interval. So that's going to be, I think it's 2.56 from memory. So it's going to be right probability, which is 1 left over, half on either side. Yep, 2.56. .63 times 0.37 over n. Right, so all we would do now is just run a solve on this. That equals that times so n equals 490.46, so about 490 people need to be in the survey. Okay, and if we have an n value of 490, what that will do is decrease that margin of error. Okay, so that margin of error will drop to that. Alrighty, all right, almost there. So Here's VCAR 2016 exam 2. This would be the first exam with stats on it. So let's just see what the question is. So it's G, it's part of a probability question. So the laptop supplier finds that in a particular sample of 100 laptops, 6 of them have a battery life of less than 3 hours. So P hat equals that. Determine the 95% confidence interval for the supplier's estimate of the proportion of interest. Give values are correct to 2 decimal places. So this is 1 mark. So this is straight into stats on this one. So, oh, that's not stats. There's stats there. So 1 prop Z. We want the 95% confidence interval, so 95. The number of laptops is 6 out of a possible sample size of 100. And there's our interval. To 2 decimal places. Done. Right, so surprising that they give you 4 lines of working out. Sort of implies that they want you to use the formula or something. You could use the formula, but it's no need. Just slam it into the calc, 1 prop Z. That's what it's there for. Okay, the 95% confidence interval for the proportion of ferry tickets that are cancelled on the intended departure day is calculated from a large sample to be this. The sample proportion, so we want to find out what P hat is. P hat will sit in the middle of these 2 values here. So all we need to do is just average them. 0.121 divided by 2. We got it. So there it is. Stats is finished. 4 lessons there. You might have thought you get to the end of the course and they might ease up, but that's certainly a tough one there. Exercise 17D is tricky concepts. Not many questions. In the end of that, there's only 6 questions, but the key is to understand it. Then you're on to the chapter review, and really now looking at just lots and lots of exam questions. Good luck, guys.